Hi students, this is 11.1 inverse functions, and this will be your lesson today. This section is about inverse functions. We're going to learn what is an inverse functions, which functions have inverse functions. We're going to learn the graphs of inverse functions compared to the graph of the regular function. And then lastly, how to algebraically solve for an inverse function given a function. What's he talking about? I don't know. Well, that's why I'm making the video, right? So let's start out with just, I guess, a conceptual idea what a inverse function does. An inverse function we usually call f inverse of x. Just a heads up, f inverse of x is not 1 over f over x. That does not mean just take your function and divide it, or take 1 divided by your function. An inverse function undoes the original function. So let me give you an example of a function and its inverse. So if I had the function f of x equals x cubed, what is the inverse function of, in this case, x cubed? So what undoes cubing a number? So if I take a number, cube it, how do I get back to that original number? Good. I take the cubed root. Good job. And it is indeed the inverse of the function x cubed is the cubed root of x. Not all functions have inverses, at least inverses that are true functions. And let's maybe look at this relation I'm about to show you on the next slide. So we'll maybe look at two different situations here. Let's start with the top. So let's say I had, so this here is going to be my domain. This is going to be my x values, for instance. And this will be the range, or after putting an x into my function, what the number spits out. And same thing down here. This will be my domain, and this will be my range. I haven't yet defined what this function is. So let's say this is the relationship. We'll just call this f. And let's say if you put in the number 1, it spits out the number 1. But if you put in the number pi, maybe it spits out the number 5. And if you put 4 into this function, it spits out the number 7. And if you spit in the number 7, if you put the number 7 into the function, it spits out the number 4. So does this have a true inverse? And here's what we're looking for. If I start backwards now, if I start with the number 4, is there one number that maps that 4? Can I get my original number back using 4? Yeah, it's just 7, right? Okay, how about the number 1? Can I, if I have the number 1, as my range or my y value, could I get the number 1? Can I find the number such that that equals 1? Yeah, it's 1. I could just work backwards. Same thing with 5. I could just go backwards to pi, and going back here with 7, I can go back to 4. No problem whatsoever, right? Right. Okay, well, let's look at maybe the second example down here. Maybe if I put the number 1 in, it spits out the number 4. And if I put in the number 5 into my function, it spits out the number, if I put in the number pi in my function, it spits out the number 5. In this case, if I put in the number 7, maybe this also spits out the number 5. And lastly, if I put in the number 4, it spits out the number 7. So can I work backwards here for all numbers? So if you give me the number 4, for instance, can I, in the range, or say that's my y value, can I find some value of x such that y equals 4? Yeah, in this case it's just going to be 1, right? Well, what about 5? So what number equals 5? Oh, well, now there's 2. It's either pi or it's 7. Which one is it? We don't know, do we? Or is it both? Well, if it's both, it violates the general principle of what we said a function was to begin with. If you recall, the idea about a function is if we put in one value of x, we get at most one value of y. That is either one or no values of y. Also, what you recall is the vertical line test. A function has to pass the vertical line test. So we're going to see how this all plays out. So what we're going to need to for a function to have an inverse is the function has to be what we call one-to-one. And a one-to-one function is a function where every value of x has at most one value of y. And one value of y has only one value of x. So one-to-one function where one value of x, where one x value corresponds to only one y value, and that's really the idea of a function. But now we're going to go and one y value corresponds to one x value. So we're going to use something on this, at least in a geometric sense. If I had a graph of the function, this needs to now pass the horizontal line test. If you recall, the vertical line test means a function is a function if it passes the vertical line test. We're going to use the same idea, but we're going to use the horizontal line test to determine whether a function has an inverse or not. So I have 4 different graphs here. Let's see if we could determine which ones are one-to-one. So again, the idea of one-to-one is that for every x value there is one y value, or at least at most one y value, and for every y value there is at most one x value. So let's look at A, and what we're going to do is we're going to do the horizontal line test. So A, does it pass the horizontal line test? So remember, the vertical line test was when we took a vertical line, for instance, and we moved it, and if it ever intersected the graph more than once, then we said the function's not a function. Well, we're going to be using that same concept, but now we're doing a horizontal line test. That is, if I have this nice straight horizontal line, and if I move it up and down the function, will it ever cross twice? Well, this one, A, no, it sure doesn't look like it. It's hard to tell what's happening right there, but that's maybe more so my drawing. But if you're a little suspicious about that little region, good for you. But let's just say it's not, just my bad drawing. So this function is indeed one-to-one. Check. How about B? Is this going to pass the horizontal line test? Who said no? Nobody said no. Everybody said no. Oh, good. No, it doesn't, because check it. Right there, it intersects twice. And what that essentially means, if I gave you whatever this y value is, say y was -3, I'd be like, hey, if y is -3, what's the value of x? Well, there's 2 possible values now, which is just too heavy for a function. How about part C? That's sneaky. Is this one one-to-one? Yeah, well, again, if we look at like some horizontal lines, we're looking, does the horizontal line ever cross the x-axis the function more than once? And even though it's got this kind of weird gap and the weird dot over there, You see that dot is the y value is unique. In fact, every single y value here is unique. So yeah, this is 1 to 1. Check. And this one's not 1 to 1. Sad. How about part D? 1 to 1? Clearly not, right? This is also not 1 to 1. How about these two relationships of points, x and y ordered pairs? Are these 1 to 1? Well, for every one value of x is there one value of y, and for every one value of y is there one value of x. Well, let's look at f. Okay, 3 and 1, 2 and 3. So far, nothing's repeated. 4 and 3. Oh, look at that. 3 showed up twice as a y value. So, in other words, if I were trying to undo this relationship, and you said, "Hey, what if y is 3? What's x?" Well, you don't know if it's 2 or 4 in this case. So, sad face for this guy. Oh, not 1 to 1. Oh. How about G? Is that 1 to 1? Yeah, it is, right? Every value of x, all the x values never get repeated. 1, 3, 4, -1. That makes it a function by itself. And every value of y doesn't get repeated either, does it? All unique numbers. So again, if you told me, hey, what does x equal if y is 3? There it is, 4. So this is 1 to 1. And now we can make a smiley face. Yay! Yay! I don't know what that was. So there's this relationship which, surprisingly, your book doesn't really go into very much. So I won't go into it too deep, but I do think it's worth mentioning and just showing a quick example. It says that if f inverse is the inverse of the function f, then if I compose f of x with its inverse, I get the identity function x. Or if I were to do it the other way around, I would still get x as well. Okay, that's kind of weird. But for example, I said that f of x, I gave you two functions and their inverses a moment ago. So f of x, we said if f of x is x cubed, then the inverse of f is the cubed root of x. So so checking this here, f composed of with f inverse of x, well, that's just the same of f inverse of x, and f inverse of x was the cubed root of x, and then the function f, we're going to take x or whatever's inside here and cube it, so that's going to be the cubed root of x quantity cubed, which is x, so that checks. But it should also work in the other direction, because we had learned earlier that when we compose two functions, f of g of x is not necessarily the same of g of f of x. And that's supposed to be an open circle over here. That's a open circle, not a closed circle. So in this case, I'm doing f inverse of f of x. And we said that that's going to be f inverse of x cubed. So that's going to be the cubed root now of x cubed. And what's the cubed root of x cubed? Just x. So it ends up working the same way. You've probably seen that before in another class. But lucky for you, our book just barely touches it and doesn't really assign you any problems. I'm going to say unlucky you. You're missing out on a learning opportunity, but you just got the learning opportunity anyway. Yay! Okay, last part of this lesson. This might be the harder part though, so don't think that it's over. This is, so given f of x, I'll say given y equals f of x, some function in terms of y, and that was an equal sign there. How to find f inverse. So I'm going to give you some steps. So typically I'll say step one. This is not in your book yet. My steps are off a little bit, but first, if it's already like y equals x something something something, you don't have to do anything. But if it gives you f of x equals something, then just replace f of x with y. Step two is the inverse step. And we're going to see more of this as we go along. But step two is the inverse step. We're going to switch our x's and y's. I'll show you all this in an example in just a minute. Step three, we're going to solve for y like we normally would. And last one, step four, we're going to replace y with f inverse of x now. So let's try one or two. Let's, for example, let's say that f of x is 3x plus 2. Let's find the inverse. Okally dokally. So I said step one is just simply replace f of x with y. The next one, this is the inverse step. This is where we actually switch stuff around. So I am going to change. I'm going to just switch everywhere there was an x. I'm going to put a y. Everywhere there's a y, I'm going to put an x. And now what I'm going to do is I'm going to solve for y. So I'll subtract 2 to the other side. And then lastly divide by 3. I'm just going to switch the order here just so I have my y on the left side. So this is my inverse function now. That's it. That's what's going to undo my value of x. So let me just really quickly explain a little bit more here. Let's use this function here. Let's just see what happens here. So let's use this relationship. I'll just do this on the side here. Say I wanted to find, I don't know, just let's find what f of 1 is. So I'm putting 1 in for x. That's going to be 3 times 1 plus 2, so that's 5, right? So the idea now is, if I were to put 5 into my inverse function down there on the bottom, it should spit out 1. It's kind of like, hey, when x is 1, y is 5. So the inverse should say that when x is 5, I should get 1. Let's see here. So if I put in, so I'm putting this in now into my inverse function down here. 5 minus 2 over 3. That's 3 over 3. That's 1. So again, the idea is the inverse function works backwards. And last part of the lesson, and we definitely need more practice with this, and I would definitely say you're going to want to practice definitely knowing what a one-to-one function is, how to, if you're given an algebraic function of f of x, how to find f inverse of x, and lastly, we're going to look at the geometric interpretation of an inverse. So given the graph of f of x, find f inverse of x. Okay, so the big principle here is that if x and y, I'll say, is on the function f, and this little symbol I just threw in there, it stands for is an element of, that is, like, if I put in x and I get some y in f, then the reverse is true for f inverse. If I put in y, so if the point xy is on f, then the point yx is on f inverse. So what we're going to see, it's kind of cool, is that, I'm just going to give you a little fact here. Fact. The graph of f of x, f inverse of x, is a reflection about the line y equals x. And also another fact, I don't have to, I can switch x's and y's to graph f inverse of x. Okay, so let's see this through an example here. So maybe here is my function. Maybe it goes like that, and maybe it starts right there. Let me put some tick marks on here. So how do I graph f inverse of x? We'll just say that's through the point right there. Well, the idea again here is, okay, so if this point, let's pick on this point because it's easy. So that's the point 0, comma, -3. If that's on my graph of f, then the point -3, comma, 0 should be on the point on the graph of f inverse of x. And so this point right here ended up getting mapped to this point over here. Sorry, my tick marks aren't really to scale, so I apologize. Let me fix those. Alright, I cheated and I added another one. But this point now, -3, 0, got mapped here. Let me show you the kind of shortcut. This line I'm about to put here, this is the one I was saying is y equals x. It has a slope of 1, 1, 1, 2, 2, 3, 3, 4, 4, and you can think of it, and it is like 45 degrees, a 45-degree angle, like it cuts the x and y axis directly in half. So what I can think about here is that this whole graph, as I was mentioning, is like a mirrored reflection. And I'm picking out a couple points here, like maybe this was the point 25, comma 0, and the point 0, comma 25 here is in here. And what I'm doing is I'm drawing here a reflection about that line y equals x. So this one right here is my inverse. And can you see how that's a 45-degree reflection, if you will? But again, as I was mentioning, if there's some point here, maybe this one, just making up a coordinate for it, it looks like it's at about 3.5, comma, what is that, 1.5. Then again, the point 1.5, comma 3.5, so that's 1.5, comma 3.5, right about there, is going to be on the line of the inverse. Okay, I'm going to do one last algebraic problem. Sorry, this lesson's going a little long, but this one was designed to be shown in class as opposed to the ones at home. So let's do one more. Let's find f inverse of x. If f of x equals, I don't know, 2x cubed minus 1. Woo, crazy. Okay, so if you recall from the steps that you wrote down, step number 1 is we're going to replace replace f of first. Before we switch, we're going to replace just f of x with y. Now the next step is the critical inverse step. I am switching my x's and y's. So x was cubed before, which means now y is going to be cubed. Now I'm going to solve for y. So let's add the 1 to the other side. So that's going to equal 2y cubed. I'm just going to switch directions here. I don't know why I do that, but I just did. So this will be x plus 1 all divided by 2. Last part, how do I get that cubed root? I'm sorry, get rid of that cube. I just gave it away, right? The cube root. So my last and final answer is that the inverse of x is going to be the cubed root of x plus 1 all over 2. And that's my answer. Hope you found this lesson informative. And again, the beauty is you can go back to it whenever you want. You can pause, you can rewind, you can, go back later and just go, okay, let me try these 2 problems on my own. So thank you. I hope that was helpful. Happy studying.